This is part 2 of lesson 6.1, Vectors in a Plane. We're going to start this part by talking about vector operations. So we need a couple more definitions. So the first one is going to be definition of a scalar. And what a scalar is, it is numbers without direction. So just a number. So we're going to multiply by scalars. So we want to make sure we distinguish between multiplying vectors and multiplying numbers. The next one is definition of vector addition and scalar multiplication. So for vector addition, if we let V be some vector that's component form is like this, whoops. And we have vector V, and in component form, it looks like this. And so there would be vectors. The sum, or it's also known as the resultant vector, so the resultant of vectors u and v is the vector. So when you add two vectors, you get a vector. So it would look like this. U plus V equals, and all you do is add the components. Oops. So U1 with V1, and then U2 with V2. Now be careful, adding two vectors is a little different than the head-tail. The head-tail resultant is taking 2 points in space and combining them to create a vector representation. But adding two vectors is literally just adding their components together. Next, the product of a scalar and a vector. And we're going to talk more about vector multiplication in a later section. So we're going to let the letter K be a real number. So it's not a vector, it's a number. So that makes it a scalar. Then what we do is we take K times the vector U. You'll see it represented in this way with the component form. And when you do that multiplication, you are simply distributing the K to each component. It's not going to change the direction at all of the vector, just the magnitude, because K doesn't have direction, it's just a number. Okay, next. So let's represent adding two vectors. Now there's two schools of thought of doing this. I personally like the tail to head. If you like the parallelogram, you'll get the same result. So whatever works for you. So I'm going to draw a vector U that's through the origin. There's my vector. That's U. So what I'm going to do to it is add V. So on the end of it, then I put some vector V. So the resultant vector is going to be from the tail of U to the tip of V. Like that. Back just a little for my pen. Oops, I forgot to write V here. So then this is u plus v. So that's a visual representation of it. So if I were to do this another way, let me draw my u. Oops. See if I can get those about the same length, since I didn't measure when I drew it. And then I draw v also, because we're representing, remember we're representing them from 0. Here's v. Oops. Oh, darn it. I had it. There we go. Okay. And then the resultant vector will be from drawing a parallelogram. So I can take this vector and I would put it here. And I will take u and draw it here. To create a parallelogram. And the resultant vector would be down the center here, would be the diagonal. There, like that. So that would be u plus v there. So either way is the correct representation of the two. Okay, so let's do an example. Let's do a couple of examples. So these are on page 464, numbers 13 and 14. So in number 13, we are going to add u and v. So we need to know what they are. U is -1, 3, and v is 2, 4. So when we add these, we are just going to take -1 and add 2, and then we're going to take the second part of v of u, which is a 3, and add the second part of v. So we get 1, 7. So that's what we get when we add the two together. In number 14, we have this operation that we have to do. So we have u plus -1 times v. So to write this out in the component form, we have -1, 3 plus -1 times our component form of v, which is this. So we do the scalar multiplication first. So we distribute that -1, and now we can combine our components. So we get -3, -1. So that's the answer to number 14. Okay, so another thing we want to talk about is something called a unit vector, and that goes along with our 0 vector. We have to have some way to represent 1, or the unit of what is the basic vector. Like when we multiply by 1, we know we don't change anything. So if we multiply by the unit vector, it has to have magnitude 1 and be in the direction of our original vector. So here's how we define it. So a unit vector of a vector, so let me just start right from the beginning here. So a vector v, a vector u with length, which would be the magnitude of u. That magnitude is 1. Okay, so then if we have another vector, v, and we know it is not the 0 vector, because that wouldn't make any sense. Why we're going to combine something with 0? Then we can define how we get u as we take any vector and we divide it by its magnitude, and we create a unit vector. So you see it written that way, literally with the vector divided by the magnitude, or because the magnitude's a scalar, a lot of times you'll see that magnitude written in front that way, and then the vector next to it like this. So how you create any unit vector is literally divide it, each component, by the scalar, which is its magnitude. So a direction vector is a unit vector in the direction of the original vector. And we have standard unit vectors, and the standard unit vector is, for the x direction, is I, which looks like this. It has magnitude 1, and it's in the direction of the x-axis. And for the y, we have j, which looks like this. It has a magnitude of 1, but its direction is the y-axis. So if you have a vector v with components a comma b, it can be written, that's the component form. The unit vector form is a, which is a scalar, times the x direction unit vector plus b times the y direction unit vector. Okay, now we have linear combinations of vectors, and all that is really just taking your, this is kind of redundant, I probably should have removed this, is just taking your AI plus BJ. So you can add vectors in that way. So it's another way to write the unit vectors. Alright, so I'm going to make a part 3 to this video because this section is rather long, and I want to make sure that I'm not overwhelming you at one point. So we'll finish this vector discussion in part 3.